All right. 11.7, catalysis. A catalyst is a substance that speeds up a reaction without being consumed itself. It's going to allow the reaction to occur at a lower activation energy. A much larger fraction of collisions is effective at a given temperature, and so our reaction rate is increased. We're going to see there's two types of catalyst, homogeneous versus heterogeneous, and that's going to affect the shape of this curve. This is one, but basically the overall idea is that, yeah, here I've got this big old EA, activation energy for our uncatalyzed pathway. And for our catalyzed pathway, it's given us a different path that's going to allow a lower amount of energy. So a higher fraction of molecules will be sufficient to overcome that barrier. Catalysts are substances that affect the speed of reaction without being consumed itself. Most catalysts are used to speed up a reaction, and they're called positive catalysts. Catalysts used to slow down a reaction are called negative catalysts. A homogeneous catalyst, all the species are going to be present in the same phase. And a heterogeneous catalyst species are going to be present in different phases. So in the iodine clock reaction, you're going to have sulfuric acid be a catalyst in that reaction. It's homogeneous. The platinum catalyst in a car, right, in your exhaust, that's going to be a solid reacting with something that's got some sort of gas. So it's a heterogeneous catalyst. Your catalyzed pathway probably is not going to have one hump like this. It's more likely that you're going to form one intermediate and then be able to form a second intermediate and then your final product. So it might have two humps in there rather than one hump. The idea is you're still getting a lower activation energy. So catalysts speed a reaction or slow it down, generally speed it up. They give the reactant molecules a different path to follow with a lower activation energy. Heterogeneous catalysts hold one reactant molecule in a proper orientation to recur, for the reaction to occur, for the collision to take place. So they're affecting that orientation factor. They're saying, hey, everybody face the quarterback when we're going to throw. Sometimes they also help start breaking bonds. So they might actually be involved in forming some of that intermediate. Homogeneous catalysts react with one of the reactant molecules to form a more stable activated complex with a lower activation energy. So if you look at this from an energy diagram point of view or from an energetic standpoint, so at a given temperature, these two distributions are going to have the same shape. Our uncatalyzed reaction is going to have a smaller fraction of molecules that are able to overcome that activation energy relative to our catalyzed one, where we move that threshold over to the left. Heterogeneous catalysts most often involve gaseous reactants being absorbed on the surface of a catalyst, a solid catalyst. So that's like your catalytic converter in a car. It's going to involve a couple of steps. 4, you're going to adsorb and activate your reactant. So adsorption is the things land on the surface, is a collection of one substance on the surface of another substance. Migration of the absorbed reactants to the surface, reaction of the absorbed substances, and then escape or desorption of the products. So in our heterogeneous catalyst in your car, carbon monoxide, hydrocarbons, nitrogen dioxide go over this sponge-like platinum surface. When they do, they're going to land on the surface, right? It's going to break up the bonds, right, between some hydrogen over here. Those hydrogens are then free to migrate over towards that ethylene, and then the output is going to be water, CO, carbon dioxide, and nitrogen gas. So the reactants are all above the metal surface. Hydrogen is adsorbed onto the metal surface, forming a metal hydrogen bond, and then it's going to break that HH bond. That absorbed molecule atoms migrate towards each other on the metal surface, forming a new carbon-hydrogen bond. And the atoms in the ethane have been completely saturated, meaning they've all picked up carbons, and so they cannot bind strongly to the metal surfaces anymore, and then C2H6 molecules escape. Enzymes are biological catalysts because many of the molecules are large and complex in biochemistry. Biological reactions often require a catalyst to proceed at a reasonable rate. So you have this big, long, spaghetti-like string of protein or polymer that's going to make up a protein, and that sequence needs to be folded in the right orientation. And if you just relied on random folding of this big, long peptide string into the right conformation, it may not get there. It may get stuck in some intermediate. And even if it didn't, it would probably take a really long time to randomly assemble that. So it's like taking a box full of Legos, tossing it up and going, hey, sometimes it's going to stick together and form my finished product. Unlikely to happen. So you're going to need this catalyst or this enzyme to speed that process up in order for it to happen at a reasonable rate. Protein molecules that catalyze biological reactions are called enzymes. Enzymes work by adsorbing a substrate reactant onto an active site that orients the substrate for a reaction. So you have an enzyme and a substrate. They're going to form an enzyme-substrate bond that's fast. The enzyme and substrate are then going to form the enzyme back again and the product, and that's usually the SO step. And you'll notice that the enzyme is conserved in this, which is what makes it a catalyst. It's part of the reaction, but doesn't get consumed. It's not a reactant. All right, so a substrate lands on an active site of the enzyme. You form this enzyme-substrate complex, and then the products are generated, and they release from the enzyme, leaving the enzyme behind as it was. So you have some enzyme and a substrate. That's our fast step. Our enzyme substrate are going to form the enzyme and product. It's a slow rate determining step. So if you've got a glucose, that's sucrose is glucose and fructose together. You got a glucose part and you got a fructose part. Well, our sucrase enzyme is going to hold these guys in the right orientation to allow this bond to be weakened. So the sucrose is in an active site. Our sucrase enzyme is going to hold them in a position where this bond is easier to cleave. And that's it for our chapter on kinetics.